Okay, in this video, I go over the homework solutions for the simulation homework. There were 3 problems, and I went ahead and solved all of those problems in one simulate file. Notice that these 3 separate pieces of code are not touching each other, so it's perfectly okay to do that since they're not interacting. You still have to be concerned about the time period, but within each model, you can still think of that as its own time period. It can be unique. So for the dock problem, my time units are in days. For the ATM problem, the first one, I did this in seconds. And for the priority problem, I did this in hours. And that's perfectly fine. They're not touching, so when I interpret the output, when I'm looking at the numbers and I'm looking at a timing system for the ATM, I have to know that's in seconds. So let's go over the problems. The first one, we have people arrive every other minute, so the time between is 120 seconds. They wait in line and then they're served. It takes 1.5 minutes or 90 seconds to serve with a 10-second standard deviation distributed normally. I had to collect the timing system and the probability that a customer will not have to wait and the average number waiting to use the machine. The second one, part B, is the one that's probably most difficult, the probability that a customer will not have to wait. That is going to be, the easiest way to get this is to look at the awaiting work percentage. The probability that a customer will not have to wait is the percentage of time from the ATM standpoint that there's nothing to work on. There's no customers there. They're the same value for just depending on the perspective. Is it the customer's perspective or the machine perspective? So if the machine is awaiting for work, then a customer's perspective is that they don't have to wait. There was a couple of clever ways to try to get to it differently. One of them was correct, one of them not so much. But this is the best way to do it. The dock problem, I went ahead and evaluated 1 dock, 2 docks, 3 docks, all within the same model. So how did I do that? Well, when I run my time between arrivals, again, it's every 1/5 of a day, or the rate was 5 a day of trucks arriving, so the time between is 1/5 of a day on average. I'm going to evaluate these 3 scenarios at the same time by doing a batching out of 3. And then the routing out using a circulate. So the first one goes there, the second one goes there, the third one goes there. But since it always batches out 3, it becomes an apples to apples. So the exact number of trucks that go this way is exactly the same that go this way, which is exactly the same to go this way. You didn't have to do that. You didn't have to do that at all. But this is a way to do this. And what we were determining and what we need is how many trucks are in the system. So I'm looking at each of the queues. These are the parking lots plus the total at the docks. So I needed all of those to come up with the total number of trucks in the system when I have 1 dock, 2 docks, and 3 docks. And then how large a parking lot to need. I also need to collect on the results of each queue the maximum. You don't want to plan to an average when you're trying to design a parking lot. You want to design a parking lot to hold close to, at any point in the day, the largest number. If you plan to the average, kind of an easy way to think of that is that about half the time you're going to run people away because they don't have a place to park. So don't plan to averages when you're talking about designing sizes to hold entities. And then the last one was a priority routing. We have 3 different types of priorities. So for each of these, I'll just pick this one. We have the time between arrivals, but I've also got to have a label that I called label priority. And so this second one I set to 2. This one is set to 3. This one's set to 4. This one's set to 1. They hit each of these servers, and then when I route out on these servers, I route out based on label. If the label is 1, it goes there, 2 there, 3 there, 4 there. And the data that I'm collecting is the system utilization, which is how busy each of these servers are. The working percentage is system utilization. Take the average of each of those, and then take the average time in system for each class. So all 4 of these, I needed to get the average time in system. So when you run your trial, it takes a little while because I'm running 3 models at the same time. There's your output. I copied that to Excel. This is what it looks like in Excel. I did a lot of editing. This is problem 1, problem 2, plus a little economic analysis on problem 2, and then problem 3, the priority rating. So for the first problem, the average queue size is about 1.2 people. The waiting percentage, the percentage of time that they're waiting for a customer show up is around 25%, and it's about 4 minutes total time in system. For the problem 2, the average queue size for 1 dock is really big. When you have 2 docks, the average drops significantly. Now that's the maximum queue size that I get. And then for 3 docks, it's really small. But when you do the economic analysis over here, so here's the cost of the docks, here's the average queue size and the average number at the docks, the average number in system, just add those up. But we've got an incredible amount of truck costs because we have lots of trucks in the system when you only have 1 dock, and the cost is real expensive. For 2 docks, it's cheaper, which is less than the cost of 3 docks. So in this case, 2 docks would be the best answer. For the last problem on the priorities, the system utilization is about 2/3, which is actually a really good system. There's not going to be a lot of waiting in general, and then when we looked at the time in system, you can see that the lower priorities were in the system just a little bit longer, even though they were arriving more often. They were lower priority, so they had a little bit longer in the system. If you would look at this, they incrementally go up. And actually, it goes quite a bit for the priority 4. Okay, that should be enough information for you to evaluate your homework and ask any questions after you watch the video. Thanks.